Let's continue with the second lecture. It's my pleasure to introduce Yifeng Liu, who will give the second talk this morning on recent advances on Beilinson-Bloch-Kato Conjecture. So yeah, I see Professor Hida and Somnath. All right, so please go ahead.
Thank you very much. Thank you for the invitation. It is pity that I cannot come in person to give the lectures, and I hope I can visit there in the future. So I will give two lectures on the recent developments on the Beilinson-Bloch-Kato conjecture, which is a higher dimensional generalization of the BSD conjecture. Okay, so let me start from the statement of the conjecture. So I will make certain simplification because this is a lecture series, right? So I'm not supposed to give a full generality. So let me start from a number field F, and I will denote by F bar as its algebraic closure. And then we consider a continuous representation rho of the absolute Galois group on a finite dimensional QL vector space. I mean, in general, we can consider more generally that the coefficient field is a finite extension of QL, but for simplicity today, we will just say QL. And such that V is geometric, so I will not give a precise definition, but in all examples below, V will be coming from some variety. And we also make a simplification that V is equipped with a polarization, which means that it is isomorphic, which means an isomorphism between V and its dual twisted by 1. And in this case, we can define an L function in the usual way associated to a Galois representation, rho V. And this L function is conjectured to have a meromorphic continuation to the entire complex plane and satisfy a functional equation centered at 0. Okay. So originally, it's only absolutely convergent when the real part of S is sufficiently large. And what does this Beilinson-Bloch-Kato, I will call BBK, conjecture say? So this conjecture predicts the vanishing order of this L function at the center in terms of certain Galois cohomological invariance of V. More precisely, the conjecture as follows. So the order of the L function at the center S equals 0 is the difference of the dimension of two vector spaces, two Galois cohomology. The first one is called H1F, so I will explain F later, FV, and minus the fixed part of V, the dimension of the fixed part of V, Galois fixed part of V. So here, this H1F is a subspace of the first cohomology of the Galois group on V, consisting of classes whose localization at every finite place V of F belongs to the local version of this one. And what is this local version? So there are two cases. Oh, sorry, here's a typo. When L does not divide V, this one classifies extensions of V by QL that are trivial after restriction to the inertia. Okay, so when L divides V, for simplicity, let's assume that V is crystalline to V. Then this subgroup H1F classifies extensions of V by QL that are again crystalline. Okay, so there is a definition more generally without assuming V is crystalline, but we will not get that because in the case we consider, this is always satisfied. Okay, once again, the first one is a typo. Okay, why L does not divide. So give some example. Let's consider an elliptic curve A over this number field F. Then there is an L-adic rational Tate module V, that is the L-adic Tate module TLA, which is a CL module of rank 2, tensors QL over ZL. So this is a two-dimensional vector space of QL equipped with the action by the Galois group of F. This is an example of polarized Galois representations considered as above. So the polarization coming from the Poincare duality of A or Weyl pairing of A. And in this case, this L function of this Galois representation is nothing but the classical L function for the elliptic curve, but translated by 1. And H0 here is just a 0 by weight, by considering weight. And H1, what is H1F here? This is nothing new, okay? Oh, by the way, this H1F is called a Bloch-Kato-Selmer group. I forgot to say. So this H1F can be obtained as the rationalization of the inverse limit of L power Selmer groups of A. Okay, so you take all L to the n Selmer group of A, and you take an inverse limit, that's a CL vector space, and you tensor QL. So you recover this subspace. They're same. Okay? So in particular, the BBK conjecture recovers part of the BSD conjecture. BSD conjecture says that the order of the L function should equal to the Selmer rank. Okay? And due to the efforts of many mathematicians since 1980s, the BBK conjecture in this case, which is the BSD conjecture, is known when F is Q and when either the order is at most 1 or the Selmer rank is at most 1. Okay. Any questions so far? Good. So we will now introduce another example or sequence examples that we will consider today, which is called the Rankin-Selberg product. Now we take a positive integer n, and we denote by n0 and n1 the unique member in n and n plus 1 that are even and odd. Okay, for example, I mean, n0 is the even one inside n and n plus 1, and n1 is the odd one inside n and n plus 1. And we write n0 as 2 times r0 and n1 as 2 times r1 plus 1. Okay, please take a note of this notation. It's elementary, but it appears very often. And then we consider 2 elliptic curves, A0 and A1 over F. And for r equals 0 and 1, we put TIL as the symmetric power of the theta module, TLAI, but raised to the ni minus 1. So in particular, this one is a CL module of rank ni. Okay, it's a rank 2, so when you take symmetric power of ni minus 1, you get a rank ni CL module. And we take TL as the tensor product of these two modules, and you twist it by 1 minus n. So this twist is to make this module polarized. Okay, so you need to twist. And finally, you take a VL to be the rationalization of TL. So in particular, this VL is a continuous QL linear representation of the absolute Galois group of F of dimension. So this is n0 times n1, which is nothing but n times n plus 1. Okay, so this dimension is quite large. When n is 1, you recover the BSD case. But when n starts from 2, it's getting larger and larger. And this is equipped with the canonical polarization because of this twist. And moreover, in this case, we know that this LSVL, this L function is independent of L. Okay, so we will just simply denote it as LSV. Okay, here is a main theorem of this lecture, which is also a theorem obtained from 2 major progress in this number theory and arithmetic geometry in recent 5 years. One is the work of Yichao, Tian, Liang Xiao, Wei Zhang, Xinwen Zhu, and myself on the Beilinson-Bloch-Kato conjecture in high dimension. And the other is the work of Newton and Thorne on the modularity of symmetric power of modular forms. So if combine them together, we will have the following quite a clean result. So in the above situation, we make following assumptions. First, we assume F is a solvable CM field. Okay, and 2, we assume the CM field is not imaginary quadratic if n is at least 3. Okay, and the third, we assume both A0 and A1 are actually defined over Q rather than F. Okay, for neither A0 nor A1 has complex multiplication over F bar. Okay, and number 5, we assume they are not geometrically isogenous. Okay, So assume these 5 conditions, we have the following evidence toward the Beilinson-Bloch conjecture for a higher rank motive. So if we assume the central value is non-vanishing, according to the BBK conjecture, the Selmer group should have rank 0. And we actually prove that this is true for all but finitely many L. Okay. So let me make a comment on these 5 conditions. The first one is because of so the first one and the third one is to make sure a certain modularity result mainly due to Newton's song. And the 4 and the 5 is a limitation of our method. Okay, it's a limitation of our method. Number 2 is the least serious condition. It essentially can be moved, but it is not removed because we lack something in literature now. Okay, so this is expected to be able to remove. Okay, so 2 is not so serious, but 1, 3 is about modularity. 4 and 5 is due to the limitation of our method. Any question about statement? I think this is a quite not technical at all, right? There's no very technical conditions involved here. Okay, so the lecture, the goal of this lecture is to explain the proof of this theorem. Okay, so now, so first so the goal is the following. I will just go in the direct way, which means that first we give a strategy how to prove something like this. Then we provide the necessary ingredients in this strategy. So the strategy requires lots of things. Okay, we first explain the strategy, then we explain how to provide those ingredients in the strategy. So first, let me explain the strategy of bounding Selmer group, which is actually due to Kolyvagin many years ago, but this is in a much more general manner. So from now on, we will just regard A0 and A1 as EV curves over Q. And we let sigma be the set of prime factors of the discriminant of F and also the conductors of A0 and A1. Okay, so basically sigma is the set of prime factors where something is bad so far. Okay, and we take a prime number L. Recall that our theorem excludes finitely many L, right? So the first thing we exclude is that we want this L does not belong to sigma. In particular, both A0 and A1 have good reduction at L. And we introduce some elementary terminology. So if we consider, so below we will consider finitely generated CL module X. And for a non-zero element, little x in X, we define the divisibility of X to be the largest integer D such that X is equal to L times L to the D times some element from X. Okay, so it is something times L to the D. So it's called a divisibility. So I think it's quite intuitive, the terminology. Now we explain a strategy for showing the vanishing of the Selmer group, which is originally due to Kolyvagin. The proof is by contradiction. We suppose, on the contrary, that the Selmer group is not zero. Okay, it's not zero. Then the first step, we can take a non-Gaussian element S of the integral version of the Selmer group, which is defined similarly, and is of zero divisibility. This is possible because of this condition, okay, of zero divisibility. Then, as a fact, one can show that the local component of this S in every place V is a torsion element for every non-Archimedean place V of F above sigma. Okay, that's an easy Galois cohomological computation. And for every, and then given notation for every integer m, at least one, we denote by Sm the image of S in the torsion version of this finite, in this cohomology group. So it's TL tensor C over Ln. Okay. Step 2, for each n, as above, we need to find sufficiently many primes P of F plus, I didn't say what is F plus is the totally real subfield of F. Okay, F plus that is inert in F, and not above sigma, not above L, such that this unramified part of this Galois cohomology at P is a free C mod Ln module of rank 1, and that the local component of Sm at P is also an element of zero divisibility. Okay, this is can be proved by some. So first you have to choose some P, which we will do slightly later. And for those P, it is not hard to show the two properties. It is not hard to find such P once we tell you how to construct them. And the step 3 is that suppose that L is sufficiently large, which we will explain in more details later. And for certain P, as in step 2, we will construct an element called Cm, which is also in this first Galois cohomology of the torsion Galois module, satisfying the property that the V component at every L-adic place V is crystalline, and that the image of the P component of Cm in the singular quotient of this Galois cohomology has bounded divisibility. Okay, which means this boundedness is independent of M. Okay, so even you raise M to 100, the boundedness, which means that it is always just L to some bounded power times some element, even when you raise M to large power. Okay, and that this V component is unramified if V is not P and is not above sigma and L. Okay, if you think carefully, these 3 things together will give you contradiction. Okay, so it is okay. By the way, so far we haven't used the condition that the L value does not vanish, right? So where is it used? Actually, the construction of Cm in step 3, in particular, this property with bounded divisibility, is a consequence of this condition, and this is the key. I mean, basically, the whole point of the proof is to relate this thing and this thing. Okay. Now, combine the 3 steps, we see a contradiction because you can consider the Tate duality pairing of Sm and Cm. First, on one hand, we know that since both the Sm and Cm come from global cohomology, the sum of local pairing should be 0. But locally, at P, at places V above sigma, this one is torsion, and this one is unramified. So when you pair them, it is a bounded torsion. Okay, it is bounded torsion, and away from at places above L, this is crystalline. This is also crystalline, so the pairing is 0. However, at P, this one has the 0 divisibility. This one has bounded divisibility. So when they pair together, they will have a bounded divisibility. But when M goes large, an element with bounded divisibility will have torsion order larger and large. So it's a contradiction, right? Away from P, you have bounded torsion. But at P, as long as M is large, the torsion, the exponent of this torsion element will get larger and larger. So they sum up, if you sum them together, you will not get 0. That's a contradiction. Okay. So this is the basic idea. It's not that complicated, but somehow it's really powerful. This idea originally due to Colivati. However, this is not possible. Any question for this strategy, please?
Hello. Yeah.
Yeah. Yes.
What do you mean by singular cohomology? This is a certain subgroup of the Galois cohomology?
It's the quotient. It's the quotient of H1 by H1n.
Oh.
Yeah. 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 You know, for the local Tate pairing, H1n is it's a Lagrangian subspace, right? H1n pair with itself as 0.
Yeah.
So the pairing factors through H1N and H1C. Okay, so now you are pairing H1N here is a free C over L module of rank 1. H1C is also a free C mod Ln module of rank 1. And this element has 0 divisibility. And this element here has bounded divisibility. So the theta pair is a perfect pairing between this one and this one, right?
Thank you. That helps a lot.
Yeah. So if you pair them together, you get an C mod L. You get an element in C mod L to the n with a bounded divisibility. So that one. So once you bound the divisibility, which means the exponent will get large when m gets large, right? Okay.
Zero divisibility means divisibility for d equals 0. It's not divisible.
It's not okay. For example, if here is also 0 divisibility, which means this element is invertible. This element is also invertible. It's a basis.
It's a basis element. Yeah.
Yeah. An element of 0 divisibility is a basis here. Okay. So yeah, because it will not divisible divided by L. Okay, so let's continue.
Yes, please continue.
Okay, so we will make some. Okay, I will gradually make more and more assumptions to limit the technicality of this lecture. So to further simplify our lecture, from now on, we will just assume that F is not imaginary quadratic, and we make a further assumption that F contains an imaginary quadratic field F0. Okay, I mean, this is the assumption. Basically, many people just assume, but we don't need it. But for simplicity, I will still assume from now on. And again, we let F plus, sorry, it already appeared here. Appeared somewhere, okay. Here, yeah. F plus be the maximal totally real subfield of F. In particular, F plus is not Q by this condition. Okay. So let me introduce what are these primes. So we now introduce this candidate primes P in step 2 and 3. Now we will take a prime number L satisfying L1 and the following set condition L2. We assume that the joint image of the Galois group in the L-adic Galois representation of this two Elliptic curves A0 and L1 to be as the maximal possible one. So what is the maximal possible one? That is the subgroup of pairs. So the element here is a 2x2 matrix with a 2x2 invertible matrix with entry in CL. Here is also a 2x2 invertible matrix of entries in CL. And the maximal possible one is the subgroup of a pair of elements with common determinants. Okay. Sayre's theorem tells us as long as A0 and A1 are not CM and are not isogenous to each other, L2 is satisfied for all but finitely many L. Okay, that's Sayre's classical theorem, famous theorem. Okay, this is the place we use the third and the fifth condition in our main theorem. Okay. I mean, actually, it is the only place we use it. Okay, let me give a definition of level raising prime. This is a slightly technical. I will explain. So we say that a prime P, a rational prime P, is a level raising prime with respect to the power L to the m if the following four conditions are satisfied. The first one, P is odd, and P is inert in the imaginary quadratic field F0, and it splits completely in F plus. So inert in the imaginary one and splits in the totally real one. Okay. And we want the AP number of the first elliptic curve satisfying this level raising condition. I mean, this is a well-known condition. It's a square is congruent to P plus 1 square modulo L to the m. And we want the third condition that L does not divide P and does not divide this product. Okay. For people who are familiar with those finite Lie group, you will immediately realize that P3 is equivalent to saying that L does not divide the cardinality of the finite unitary group of rank N0 over Fp. Okay, this is exactly the factors of the cardinality of that finite unitary group. Okay, the last one is quite technical, so I recommend you not to read this. So this basically says that, okay, this condition is about the Sadaka parameter of the other one. The other one, A1. This basically says that if you raise the Sadaka parameter to the symmetrical power n1 minus 1, it should be, there should not be extra relation times p. So there should be, for example, if n1 is 3, then if we say the two roots of APA1 is alpha and beta, then you take symmetrical square, it's alpha square, alpha beta, and beta square, right? And we know that alpha beta is 1. And this condition basically says that alpha square is not 1 mod L, beta square is not 1 mod L, and they are also not minus p mod L, also not minus p over, also not p over L. Just saying that there will be no extra congruence condition in terms of p. Okay, so I will not give precise more analysis to this condition. So in some sense, P2 gives you some level raising for this A0, and the P4 gives you some genericity because it's a non-divisibility condition. Okay, it's a genericity condition for the other epoch of A1. So A0 and A1, they play very different roles, very different roles. Okay, we have two assertions concerning level raising primes. The first one, for effectively sufficiently large L, by the way, satisfying L2, okay, there exists infinitely many level raising primes with respect to Lm with positive density for each m. This is a consequence with triple tariff density, a very sophisticated application of triple tariff density will give you this thing. And by the way, you will ask, why do we need a sufficiently large L? Because, for example, we at least need some prime p satisfying P3, right? If all prime factor will not, if, for example, where L is small, it is possible that there's no such p at all. Okay, of course, there won't exist such levels in prime. So as long as you exclude those elementary obstruction, you can always find sufficient infinitely many such level raising primes with positive density. And the second one is a consequence of P2, P3, P4. I mean, actually everything. It is that, recall that in the strategy, we need that this H1n to be a free C mod Lm module of rank 1, right? This requires something. It's usually wrong. Okay? And P1 to P4 will ensure that for every prime P above a level raising prime, the little p, with respect to Lm, the C mod Lm modules, both of them, and H1n, and hence the H1 which is the dual of H1n, they are both free of rank 1. Okay, that's a good exercise to prove 2 from P1 to P4. Okay. Any questions so far? Okay, good. Now, so recall that in the main theorem, there's a non-vanishing of the central L value, right? So how does this non-vanishing of central L value imply anything? I mean, what does it say? At least it should say something, right? So what is the consequence we need from this non-vanishing condition? And this is our automorphic input. And by the way, so before saying that, let me first give you some. So where does automorphic form come from? this is actually, we need lots of modularity theorem. So first is the modularity of rational Elliptic curves, which is due to Wiles, Taylor Wiles, and many other people long time ago, together with a recent breakthrough of Newton and Song on the automorphy of symmetric power of modular forms. And we also needed the cyclic automorphic base change, also known several decades ago. Combining these three ingredients, we know that for every I either 0 or 1, there's a unique opto-isomorphism cuspidal automorphic representation pi called Ni of GLNI-AF, satisfying the following condition. So first, for every p-adic place V of F such that AI has grid reduction at P, this pi Ni, the V component of pi Ni, is a ramified principal series with Satake parameter that is basically the symmetrical power of this alpha P, beta P, where alpha P, beta P are the roots of the Satake polynomial of the EB curve, original EB curve. And this FV is the residual extension degree of FV over QV or QP. Okay, and that's the condition for those V. In fact, this condition already specified this pi and I uniquely by the strong multiplicity one. But for your convenience, let me get one more condition. So how about the Archimedean place? So for every Archimedean place, which is automatically complex, because F is CM, this pi and IV is the principal series of characters. I mean, at Archimedean place, at complex Archimedean place, every irreducible or admissible representation is a principal series. And this is the principal series of these characters, arg and I minus 1 and I minus 3, and blah, blah, to 1 minus ni. So this arg is the so-called argument character. So at the send C to C over square root of the norm of C. Okay, we know the following properties. So first, the field of definition of pi and I is Q. Okay, and the second, the previous L function of the Galois representation V is nothing but the automorphic L function of the Rankin-Selberg product pi n and the pi n plus 1, translated by half. Okay, now since the field of definition of pi n is Q, this Satake parameter of pi n for n is either, for the large n is either in n or n plus 1, give a homomorphism phi n from Tn away from sigma to z. So this Tn away from sigma denotes the abstracted spherical Hecke algebra of the unitary group of rank n away from sigma. Okay, so you get some Satake homomorphism. Okay, any question so far? The notation? Okay, good. So now I will explain the consequence of the non-vanishing of L value. So this is also known as the Gan-Gross-Prasad conjecture, but I will now only state a weaker version that is enough for our purpose. So first, due to the recent breakthrough on the Gan-Gross-Prasad conjecture by Buzat-Plessis, myself, and Wei Zhang and Xinwen Zhu, I mean, together with lots of previous work. Okay, this is the final attack, but it of course is built on many previous works on the GGP conjecture. So what does this GGP conjecture say? It says that we can find the following data. So first, we can find a totally positive definite Hermitian OF lattice lambda n of rank n that is perfect away from sigma. And we also can find a positive integer that is at least 3 with prime factors in sigma. And such that the following true. The first one, okay, so before looking at this, let me introduce the notation here. So what is this Hn? So here for any n is either n or plus 1, this Hn is the unitary group of this the Hermitian space defined by lambda n. So this is a Hermitian space over F. So you take a unitary group, which is a group over F plus, and you take a restriction of scalar, you get Hn. And what is lambda n plus 1? Lambda n plus 1 is just the original lambda n. You add a line here, add a line of length 1 here. Okay. And what is this level? This for a positive integer d, we denote by KND, which is the open compact subgroup of HNAD, the full level D open compact subgroup with respect to this lattice lambda n. Okay. Now it says that we can find a lambda n and a d such that you can find an element Fn that is a function on this finite quotient. This is a finite level quotient with value in C and is annihilated in it is eigenspace of this character phi n. Okay, phi n. So this Heck algebra will act on this function space, and you take the eigen element Fn, and again here you take an eigen element in Fn plus 1, and the functional is just take the diagonal sum. You take Fn(h), Fn plus 1h, and you adding over the diagonal. Okay. Okay, so the GGB conjecture implies that we can always find a lambda n and a d such that you may find some Fn tensor Fn plus 1 with a non-zero such summation. Okay. Oh, sorry. Now, in what follows, we will explain the construction of CM in step 3 with these ingredients. Okay, so for that, we will now fix a choice of the pair lambda n and d as above. Okay, so we will not change them, and the lambda n and the d will just be fixed. The later notation will not show the dependence on such pair. Okay, so any questions so far? Good. Okay, now to construct the CM. Oh, sorry.
Can I just double check that the unitary group is compact at infinity?
That's right. That's right. Because there's a positive definite. Mm-hmm.
Right, but
Totally positive definite. Yes.
It is compact because of the nature of the automorphic form being sim n somehow. So sim n of the elliptic curve makes the groups at infinity by the GGP recipe to be compact.
That's right. Exactly. Yeah. Yes. Exactly. Because the weight is exactly the one that is, how to say that, like sitting in the like 202 and a negative, like negative 202, negative 11. So they just sitting in the middle of the other one. So that one will give you the compact form. Yes. Good. So now let me to construct CM. We need to use a certain geometry. So we need to use some modular space associated with unitary groups. Okay, so we will introduce the geometry from now on. And from now, we will just fix an embedding tau 0 of C into of F into C. And we will put phi to be all complex embeddings F such that it induces the same complex place of F naught as tau 0. Okay, by the way, F naught is imaginary quadratic field containing F. In particular, this phi is a CM type. Okay, for the simplicity of this lecture, I will make a further assumption, which is usually not satisfied, but let's just pretend this is satisfied, okay? It will not change any nature, but it will make this lecture, which will make my talk much easier, okay? So we will assume there exists, and we will fix such a triple, A0, I0, lambda 0, in which A0 is an abelian scheme over OF away from sigma, and I0 is a complex multiplication of CM type phi of OF And the lambda 0 is a principal polarization of A0 that is compatible with I0. Okay, usually this doesn't exist unless f has class number 1. But let's just pretend it exists. It will not lose any generality in this talk. So now we will take a degree 1 prime f of f plus that is inert in F with underlying prime number p that's not in sigma. We will also fix an isomorphism between C and QP bar that induces the prime P through tau 0, okay? So in what follows, we will always view F as a subfield of C through tau 0. This is important. Okay, for N, that is either N or M plus 1, we define a modular space called Mn, curly Mn, over OF bracket P, the localization at P, classifying quadruples A, iota, lambda, eta, where A is an abelian scheme of dimension 2n. This iota is the action of OF on A, whose characteristic polynomial under the algebra is given by this polynomial. So it is so away from tau 0. So like this signature is like n5, but you replace one copy of tau 0 to its conjugate. Okay. And the lambda is a polarization of A that is compatible with the iota, and there is principal away from sigma and away from P. And they're satisfying that this kernel of lambda, the P torsion kernel of lambda is actually contained in this frac P. So it is killed by this frac P and has order P squared. Okay, this is the minimal possible order that is not 1. Okay. So this is not principal at P, but is the minimal, so in some sense it's minimally non-principal. Okay. And what is eta? Eta is a level D structure. I need to remind you that this is the level structure which is quite different from the one you see from, not quite different, just slightly. I mean, it's not the usual level structure you see from the PEL type Shimura variety. This is the Hermitian level structure rather than skew Hermitian. And it's defined in the following way. So this fixed triple is actually a way to turn skew Hermitian one to Hermitian one in the following way. So this is an isometry between a Hermitian module, lambda n, tensor C mod D, to home of A0 D AD. This means the D torsion, okay? And how to define how to define a Hermitian structure on this abelian group. Here, the right-hand side is equipped with a pairing. Okay, it is possible that the pairing is degenerate. Okay, it's a pairing that sends a pair of element x, y in this space, in this abelian group, to the composition of the morphism. So first, x is an element from A0 D to AD. Now you apply the polarization, it will go from AD to A check D. Then you apply the dual of y, it go back to A not check D. Then apply lambda not inverse. Okay, maybe not. Yeah, yes, lambda not inverse, because we assume it's a principal polarized. You go back to A0D. So you start from x and y, you go around, you get an element in endomorphism, and this whole process is OF linear. So you get an automorphism of A0D that commutes with OF. This can only be OF tensor C mod D. Okay, so this one is equipped with a pairing valued in OF tensor C mod D, and this one is also equipped with a pairing with OF mod CD, and we want an isometry between them. Okay, now let me give some initial properties of this moduli space. So I will denote by okay. So I will denote by any question on this page. Okay, so I will denote by MM prime as the generic fiber, which is a modular problem over F, and I will also denote by MN as the special fiber over the residual field at P. Now we record that for a point A iota lambda eta and S value point in characters P, there is a Hodge sequence of the first Ram homology of A relative over S. The quotient is the algebra, and the kernel is the differential of the dual. Okay, and because we have OF action, and since we have identified C with Q bar, this OF action, okay, how to say this? Okay, this will induce a decomposition of this OF tensor OF over P over FP module, okay, according to places to the invariance of F into C, or same as F into QB bar. And this is, so it has a direct sum decomposition in the following way. So the whole sequence, so each term has this decomposition, and the whole sequence also decompose correspondingly. Okay. Now we denote by MN circ. This is the closed locus of MN on which the tau zero component of the omega A dual, if you apply the polarization, by the way, lambda is the polarization. If you push forward this submodule along this polarization, it gets zero. This is a closed condition, and it gives a closed locus of Fn. Also, we define Fmn bullet. It is also a closed locus of Fn on which we want the kernel of polarization push forward of the tau zero bar component of H1 drum is contained in the first submodule. And by the way, this one has rank 1, and the kernel lambda star at tau zero also has rank 1. So this one means that the omega tau zero is exactly the kernel of lambda, kernel lambda star. And this one has rank 1, but this one has rank n-1. This condition says that this one-dimensional stuff is contained in this n-1 dimensional guy. So this is also a closed condition if you require a line inside a hyperplane. Okay, so both of them will define a closed locus. And we have a natural morphism over OFP sent from Mn to Mn plus 1, simply by adding this fixed triple A0 lambda 0 not iota 0 lambda 0. Okay, so by the way, so Mn is classifying those quadruple of dimension 2n, and Mn plus 1 classifying the quadruple is 2m plus 1, and the this is not 2n. This is the this is the degree of f over q times n. Not 2n. It's you should replace 2 by the degree of f. Okay, so when f is the imaginary quadratic one, it's 2. Sorry for that. Okay, so by adding A0, iota 0, lambda 0. And this rho n restricts to morphism, so it will preserve these two closed stratum. Okay, it also has the induced circle one and the bullet one. And for future use, I will denote this quotient, which has already appeared in the Gan-Gross-Prasad conjecture, just as Sn circ. Okay, you may ask me why do I put a circ here? I mean, it seems there's no circ here. So you will see the reason immediately. Okay, this is regarded as a discrete scheme over OF over P, according to the context. Okay, this is originally a finite set. And we can always regard a finite set as a scheme over a field, just in a stupid way. Okay, and we have a similar map for Sm circ to Sm plus 1 circ. Okay, now let me state some properties of this modular space. So first one, this functor Mn is a projective, strictly semi-stable scheme over OFP of pure relative dimension n-1. Okay, it's a scheme, and it is strictly semi-stable over this field of definition. This ring OF localized at P, and its relative dimension is n-1. And two, both Mn circ and Mn bullet are projective smooth schemes over OF over P of dimension n-1, and that their intersection, which I denote by Mn dagger, is smooth of dimension n-2. Okay, so what's the picture here? So this strictly semi-stable scheme. So you know that for strictly semi-stable scheme, those special fiber, if you the graph of this set of irreducible components of the special fiber, any two of them will intersect. They will intersect in the normal crossing, right? So this one is actually quite easy. There are only two groups of irreducible components, and the elements of each group they don't intersect. But components from different groups, they will intersect in codimension 1. So the intersection will be smooth of dimension n-2. So in other words, this semi-stability is just there are just two pieces of just two parts of them. So it's like kind of depth 2 semi-stable. This is the easiest one, which is not smooth. Okay, this one is not smooth, but it's the easiest one after smooth. And the scheme MM circ, this is in fact originally it's just a scheme over FP OF over P, right? But indeed, this morphism, structure morphism, factors through another zero-dimensional scheme, which is the Sn circ. Sn circ is this set regarded as a zero-dimensional scheme over OF over P. Okay, so indeed, this one is a projective bundle over Sn circ. Projective bundle, which means that it is a fibration such that each fiber is isomorphic to the projective space. Okay, and there is also a functorial relation of this projective bundle. They are compatible under two different morphisms from n to n+1. Okay, and this is the reason I put a circ over this set, because this set actually classifies the components of this strata. And this strata is easy. It is a projective bundle over a zero-dimensional Shimura set that is given by this unitary group. Okay. By the way, what is this M dagger? This M dagger is also not complicated. So every fiber here is a projective space of dimension n-1. And the M dagger should be a hypersurface in this projective space. And what is that? And you can show that the closed-up scheme M dagger is actually a Fermat hypersurface of degree p+1. So if, for example, if n is 3, then this is a Fermat curve that's defined by x to the p+1 plus y to the p+1 plus c to the p+1 equals 0. Okay, that's a Fermat curve. Okay, so what is the relation of this modular space with the Schmor variety? Okay, for experts, probably you already realize this is more or less a Schmor varieties. So what is the precise relation? And here's the following one. So we let Vm prime be the unique up to isomorphism F over F plus permission space that has signature n-1, at this default place, and is isomorphic to the Vn. Vn is the one we always use. That's the one determined by lambda n. In particular, Vn is totally positive definite. And they only different at this place and also at P. Okay, they differ at two places. So the change of, you change twice of the Hasse invariance, you still get a global one, a rational one, Vn prime. Then Mn prime, by the way, Mn prime is the generic fiber. Okay, Mn is the special fiber. So the generic fiber is a Schmor variety associated with the unitary group defined by this Vn prime of a certain level that is maximal away from sigma. And there is also together with a factorial diagram like here. Okay, I will leave the diagram to you to write on it. Okay, so I guess it's at the exact time, right? I should stop at 2 p.m. Oh, sorry, at this moment. Okay, so I will break here. So tomorrow I will continue from the next page of slides. Okay. Any questions?
Let's first thank the speaker. Now we can take questions.
To regard Mn-Circ as a scheme over Sn-Circ? How does one regard? Sorry, I did not follow.
How did one what?
How is Mn-Circ a scheme over Sn-Circ?
Okay, I didn't say. I just state a fact that it is naturally a projective boundary. I didn't tell you how to map it.
Maybe you want to give the group theoretic underpinning to the commutative diagram. Is there a group theoretic underpinning in terms of Shimura varieties?
No, it's not that. It's more complicated than that. Because you see, this Sn-Circ is not this group. Mn-Circ, okay, so Mn-Circ is a part of special fiber of this Shimura variety. The Shimura variety is this unitary group. But Sn is a different unitary group. It's this one.
It's a compact unitary group.
It's the compact one. And the Shimura variety is the non-compact one. Non-compact at infinity. Okay. So, and this map is not produced by group theoretical statement. It's produced by certain isogeny argument of the abelian variety. They both of them parameterize some abelian variety. Okay, this one also parameterize some data like before, like this one. And the map is constructed by quotient the abelian variety, this one represented by some finite subgroup, and you obtain some abelian variety represented here. So you get a map. Okay.
So although both are coming from Shimura varieties, the morphism is not coming from a group theoretic data.
Okay, the vertical ones are coming from Shimura varieties. The horizontal ones are not. The horizontal ones are coming from modular interpretation. Yeah.
There are morphisms of Shimura varieties which don't come from group theoretic data.
Yeah, there are. Yeah. Oh no, this is not all Shimura variety. This is just a piece of the special fiber of the Shimura variety. It's not the generic fiber. It's not this one.
It's not a generic fiber.
Yeah,
it's
a strata of the special fiber of this one. Okay, let me give you an analog. Sorry, I should say this one. This is a higher dimensional analog of the following well-known thing. So for let's say for modular curve, if you take a prime p, that is a grid reduction. You take a gamma n level and you take a p that is not n, not divide n. So and you consider the super singular points of reduction at p. Then those points are parameterized by a definite quaternion algebra, right? So this one is analogous to that phenomenon.
All right. Okay. So it's a very characteristic P phenomenon.
Yeah, exactly. That's a characteristic P phenomenon. Yes.
Anyone else? Yeah.
I have a simple question. Can you go to page number 3?
Number 3. Yeah.
Yes. So here TL, you are tensoring two symmetric power representations, and then you are taking some twist by 1 minus n. Is there a specific reason why you need to take this particular twist?
This is to make sure this one is true. If you don't take twist, that this one is like a 2n or something, 2n minus 1, I guess. Here.
I see.
If you don't take twist, it will be another number. I forgot which one.
I see. There is a paper by Loeffler-Zerbes where they do symmetric square of a modular form, and there also they take twist by non-trivial Dirichlet character, and there they mention that their paper won't, the arguments won't work if they don't take that twist somehow.
Yes.
Right. Okay. Right.
You had some questions?
Here we took the symmetric powers, the n and n plus 1. Could we take any two integers, n and m, and play the same game?
Technically, no at this moment. So so you know there's a Rankin-Selberg. The automorphic Rankin-Selberg works for any pair of rank, right? For any GLA times GLB, you have an automorphic one, right? But now you want to do some arithmetic story of that Rankin-Selberg product. At this moment, we only know how to do for GLN times GLN plus 1 or GLN times GLN. The rest of the cases are still in mystery. For example, we don't know how to construct a meaningful cycle if you take GL1 times GL4, for example. Okay, so it is still, I mean, this is a very good question. I mean, many people have thought about it, but no good answer so far.
I see, thank you.
Anyone else?
Just one more, the hypothesis for if A naught, sorry, the same page, page 3. If A naught and A1 both have CM by the same field, should it be somehow simpler?
Then the large image L2 will not satisfy.
But I mean, maybe some other method, like somehow GL1.
You're right. That's actually, then you have to go very carefully to every place where we use this large image hypothesis. It is possible. I didn't rule the possibility that, you know, I mean, we have to check very carefully at every places. We have used this large image condition, a consequence, at many places. So I wouldn't immediately say no, but of course you need something to I don't know if probably no. Probably if you use if you have CM by something, I don't know. I mean,
maybe just if they had like coming from just Heike characters over the same CM field or imaginary quadratic.
Oh, but if over the same CM field, that's definitely no. But if it's if A1, A0 have a CM over a different F, not this F, then possibly one can say something.
Yeah, thanks.
You know, I just wondered that the theorem of Newton and Thorne is the one I saw is for globally unramified representations. Level 1.
Level 1. No. There's they have two papers. There's the second one solves all modular.
So any level is allowed?
I think so, yes, but only over Q.
Any level is okay. Okay, good.
Yeah, originally they only say everywhere grid reduction, then you don't have weight 2, right? Then later they say they can prove weight 2, but for semi-stable. But finally, they can do any level.
Any level. Okay.
Mm-hmm.
So what happens if the order of the vanishing is exactly 1, I mean, L function?
That's a good question. We also have a partial result toward a rank 1 case, but so in the Kolyvagin story, I mean in the BSD, how people prove that if the L rank is order is 1, then you prove some hidden points is non-vanishing. Then use that hidden point, you show that the Selmer rank is 1, right? And here, we so far we are not able to show that if the so at this moment we cannot show the Gross-Argyll part, but we show the Kolyvagin part. So we show that if the element of the diagonal cycle in the Selmer group is non-vanishing, then the Selmer group has the has rank exactly 1. That we proved. Okay. But for the first half, the Gross-Argyll part, in this case, in the Rankin-Selberg case, it's still open.
I see.
Are you going to upload your slides?
Yes, I will correct typos and but upload tomorrow after tomorrow's talk because these two are combined together.
Yes. Okay.
Yeah.
Fine. Good. All right. So if no more questions, let's thank Yifeng again. And
Thank you.
We look forward to your lecture tomorrow.
Thank you. See you tomorrow.
Bye.
Bye.